Okay, let's take a minute and review what we know about bonding, orbitals, and shapes, the stuff we've been talking about in class the last few days. Okay, and we want to start with making sure we understand what an orbital is. And we think of an orbital as the space around the atom where the electron probably lives, because an orbital is really a probability. It gives us the place where an electron will be 90% of the time, and from experiments we can calculate that fairly accurately. So you see in this picture that we have the shape or the probability of an s orbital. So we really think of the s orbital as this denser part, but there's also times that it's not there. And then we have the p orbitals, the px, the py, and the pz. Electrons, because they're both negative, don't want to live in the same general area, so they try to spread out and use all the available space to minimize the negative repulsion. Okay. We also need to know that orbitals have energy, and the 1s is lower than the 2s, which is lower than the 2p, and so on. And you may remember that where the orbitals are is attached to the periodic table. This is the s block, this is the p block, this is the d block, and this is the f block. So I can see that hydrogen has 1 electron, it would be 1s1. Helium has 2, it would be 1s2. Lithium has 3, so that it would start to fill 2s1, 2s2. The 2p's would then fill, then the 3 s's, then the 3 p's, and so on. And this shows you, without the elements actually on there, how the periodic table relates to orbital filling and then orbital energy. Okay, so we're going to take a closer look at the carbon atom, and I can see from the periodic table that carbon has 6 electrons. It has 1s electrons, it has 2s electrons, and it has a 2p1 and a 2p2. So if we look at carbon's electron configuration, we can see it's 1s2, 2s2, 2p2. And if we look at that in terms of energy, we can see I've got 2 in the 1s, which is lower in energy than the 2s, where I have 2. And my 2p's all have the same energy, so the electrons don't pair up until they have to. And if we really think back to last year, these electrons are spinning, and so if they have opposite spin, it helps them go in the same orbital together. Charged particles that spin make little magnets, and so this one would have a north up here and a south at the bottom, and the other one would have the south and the north opposite, and that would be a magnetic attractive force. So that's how the electrons can force themselves to live in a tiny space, but they don't do that unless they have to. Okay, so I want to stop for a second, and we're going to look at what these orbitals actually look like in Odyssey. Okay, so in Odyssey, I can look and I can say, okay, here's my 1s, there's 2 electrons that live there, and there's 2 electrons that live in the 2s, and there's an electron that lives in the 2p, and there's an electron that lives in the 2py, but there's nothing in the 2pz, it's just empty space. Okay, if I want to look at that as a cross section, the 1s is there, the 2s is there, and these are just probable regions where the electron is. There's the 2px, the 2py, which I have to spin a little bit to see, and the 2pz. Okay, now talk a little bit about those electrons, and we want to say these are the core electrons, and then these 4 electrons here are valence electrons. And we know that valence electrons can be involved in bonding. So carbon has 4 electrons that it could share. And if we wanted to look at carbon bonding with 4 different hydrogens, because each hydrogen would have 1 electron to share, I should get 4 bonds. But when I think about where the electrons are on carbon, I've got 2 in the 2s, I'm not going to draw the 1s. And then I've got my px and my py, and then I'd have pz coming out of this axis. Well, I've got 2 electrons in this orbital, 1 here and 1 here. So if my little hydrogens, and their hydrogen just has a 1s electron, so I have 4 of these. If I try to bond these right now, I've got 2 problems with that. I know that a carbon to hydrogen bond, and we can test this in Odyssey, they're all the same energy. But I've got electrons here that have different energies with them. These 2 have more energy than these 2. I also know to bond, I'm going to share an electron with an electron. But these are already 2 guys who are very happy with each other, and I've got 2 who could share here and nothing here. Okay. If I were to look at the shape here, and I were to say, well, let's go ahead and bond a hydrogen here and a hydrogen here. Then I would have a molecule that would have a 90-degree angle, because I've got my px and my py, and I'm putting one here, I'm putting one here. That's a 90-degree angle. And we know from experience that the water molecule is not at 90-degree angles. And that would leave a lot of space over here with nothing. So we have a little bit of a problem, and the model that we're developing doesn't really explain what's going on. So let's look at what happens with carbon so that it can actually bond. So the first thing that happens is the orbitals say, I want to rearrange. We want to live in different spaces. And I need 4 places that all have the same energy. Well, I'm starting with a 2s and 3 2p's. So this is what the orbitals look like on the atom. What might they look like on the molecule? Well, what if I took all of these, and this is what we did with the Play-Doh, mashed them together and made 4 new orbitals that are all the same energy. Then when the electrons distribute themselves, they're going to spread out. So I have 4 new shapes, 4 new probabilities, 4 new energies. The energy is somewhere between an S and a P, and we're going to call this an sp3 orbital. And we're going to put a 2 in front because it came from the second energy level. It was 1 S and 3 P's. So it's 1 part S character, 3 parts P character. And the shape of those molecules, or those orbitals, they are going to organize themselves in the available space around the atom. And I'm not good at drawing in 3 dimensions, but there would be one back here in the back. Okay, so that now this angle is 109 degrees. And I've got what I call a tetrahedron. More importantly, I've got single electrons in each of these spaces. So now when my hydrogens come along, I can share one here, and share one here, and share one in the orbital back here, and share one here. So I essentially get a shape like this. My hydrogens are here, my oxygen is in the middle. And the model of orbitals with the same energy aligned in 4 different spaces or 4 different probable locations is consistent with the molecular geometry that we actually see.